The prevailing view among the majority of scholars is the Big Bang theory, which is the principal explanation for the creation of the universe. This theory addresses the emergence of stars, planets, and all forms of life, including humanity. Although its name may seem somewhat whimsical, the Big Bang provides a comprehensive account of what might have occurred in the early stages of the cosmos. Originally, the universe was a highly condensed point, smaller than a pinhead, with particles packed tightly together. From this extremely compact state, an enormous explosion of matter and energy took place, known as the Big Bang. This event, which occurred billions of years ago, marks the beginning of cosmic history. However, recent scientific advancements have revealed contradictions to the original predictions made by the Big Bang theory. When NASA launched the James Webb Space Telescope, JWST, the largest and most sophisticated space observatory ever built, researchers anticipated its observations would affirm the Big Bang theory. However, after only 1 year in space, the telescope surprised scientists with its remarkable ability to probe the universe's early past. The JWST's groundbreaking capabilities have uncovered galaxies that date back so far in time that they challenge current models of the universe's origins. This discovery has sparked intense research into what may have existed before the Big Bang. A pivotal moment in this exploration occurred when astronomer Rohan Natu, analyzing data from the telescope, discovered a galaxy that dates back only 300 million years after the Big Bang, making it the oldest galaxy ever identified. This discovery sent shockwaves through the scientific community, demonstrating the transformative potential of the JWST. Its mission to revolutionize our understanding of the universe has only just begun, with promises to unlock unprecedented insights into the earliest periods of cosmic history. The discoveries made by the JWST challenge previous expectations and uncover galaxies that exhibit characteristics far beyond what was originally predicted. These unexpected findings have prompted a rush of scientific inquiry, pushing researchers to reconcile these observations with established theories. As scientists grapple with these discoveries, they are faced with fundamental questions about the nature of the universe and the forces that shape its evolution. Additionally, the technology used by the JWST is groundbreaking. Positioned 1.5 million kilometers from Earth, it is shielded from earthly interference and kept close to absolute zero by its sunshade, which is the size of a tennis court. The telescope features a large segmented mirror and highly sensitive instruments designed to observe aspects of the early universe that have never been seen before. This era, known as cosmic dawn, occurred within a few hundred million years after the Big Bang and represents the time when the first stars and galaxies began to take shape. The process by which this cosmic transformation occurred is still being intensely studied, with theories ranging from the influence of dark matter and dark energy to the interactions of starlight, gas, and dust. The JWST's observations of galaxies from this early period offer cosmologists a unique opportunity to test their theories. By closely examining these ancient galaxies, scientists can either confirm their existing models or discover new gaps in their knowledge that may lead to groundbreaking revelations. Initially, it was expected that the telescope would only find a few faint and small galaxies. However, the reality exceeded these expectations. The telescope's first images of the distant universe revealed numerous galaxies, each with ages, sizes, and luminosities far surpassing earlier predictions. This abundance of early galaxies has set astronomers into a frenzy, with new records for the earliest discovered galaxies being broken daily. This has led to a re-evaluation of our understanding of cosmic history. In the wake of these findings, theorists and researchers have worked to explain the existence of these surprisingly mature early galaxies. Some speculate that errors in the analysis of the initial data might explain the unusual findings. Nevertheless, the consensus remains that these results indicate a significant shift in our understanding of the early universe, offering tantalizing clues about cosmic evolution. The recent revelations from the JWST about early galaxies have raised profound questions about the very nature of the universe and cast doubt on established cosmological models. Some scientists wonder whether these findings can be reconciled with traditional theories, while others suggest they may be the first sign that the universe is even more intricate and unusual than previously believed. At the heart of these questions lies our fundamental understanding of how the structured universe we observe today emerged from the chaos of its primordial state. The early findings from the JWST have the potential to completely rewrite the opening chapters of cosmic history. They may not only provide insights into distant epochs and remote galaxies, but also shed light on the origins of our own Milky Way galaxy. As Mark McCahon, Senior Advisor for Science and Exploration at the European Space Agency, aptly stated, You build these machines not to confirm the paradigm, but to break it. You just don't know how it will break. The origins of the JWST trace back to the Space Telescope Science Institute in 1985, even before the launch of the Hubble Space Telescope. At that time, G. Weir, then the deputy director of SSI, was tasked with imagining what the next generation of space telescopes might look like after Hubble. Despite initial reservations, Weir and a small team began the groundwork for what would ultimately become the JWST. Unlike Hubble, which primarily observes visible light, the JWST was specifically designed to observe infrared light. This ability allows it to peer much deeper into the universe, which is essential for studying ancient galaxies whose light has been stretched into the infrared spectrum due to the expansion of the universe, rendering them invisible to telescopes like Hubble. With its large, cold, star-like mirror, the JWST was perfectly suited to explore the mysteries of cosmic dawn. The necessity for the JWST became apparent in 1995 when the Hubble Deep Field observations revealed a multitude of galaxies in what was previously thought to be an empty region of space. This discovery hinted at the richness of the early universe and reinforced the need for a telescope capable of probing even deeper into cosmic history. After more than 2 decades of development and an expenditure of approximately $10 billion, the JWST was successfully launched on December 25, 2021. By July 2022, it was ready to begin its inaugural year of scientific research. Early projects like the Cosmic Evolution Early Release Science Survey and the GRISM Lens Amplified Survey from Space were specifically designed to investigate ancient galaxies. Though initial forecasts were modest, the results far exceeded expectations. Observations from the JWST have called into question long-held beliefs about the early universe, uncovering galaxies that defy traditional models. These surprising discoveries underscore the importance of pushing the boundaries of scientific inquiry and highlight the transformative power of advanced technologies like the JWST. As researchers continue to unravel the universe's mysteries, they are on the brink of reshaping our understanding of cosmic history and the forces that have shaped the universe into its current state. The early observations from the JWST astonished astronomers by revealing extremely distant galaxies. Before the JWST launch, the farthest known galaxy, GN-Z11, was identified in 2015 with a redshift of 11, corresponding to a cosmic age of approximately 400 million years. However, following the initial set of JWST observations, Rohan Natu and his team, along with other independent groups, made a groundbreaking discovery. They identified a galaxy named GLASS Z13, which has a redshift of 13, appearing about 70 million years earlier in cosmic history than GN-Z11. The rapid pace of these revelations was facilitated by new methods for estimating redshift, which, while less precise than direct measurements, enable quicker evaluations of a galaxy's distance. Unexpectedly, GLASS Z13 appeared exceptionally bright and massive, with a stellar mass comparable to billions of suns, despite being much younger than the Milky Way. Subsequent observations revealed even more astonishing findings. Dozens of galaxies with redshifts as high as 20, indicating their existence merely 180 million years after the Big Bang. Some of these galaxies exhibited distinct structures, a feature not expected to appear so early in cosmic history. Moreover, evidence emerged of galaxies similar in size to the Milky Way at a redshift of 10, less than 500 million years after the Big Bang. These rapid advancements challenge predictions made by the standard cosmological model, known as lambda cold dark matter, lambda CDM, which explains the evolution of the universe based on dark matter and dark energy. According to this model, such massive galaxies should not have formed so early in the universe's history. The appearance of such large galaxies in the early universe presents a significant challenge for cosmologists trying to understand the puzzle of cosmic evolution. To solve this mystery, it is crucial to study the early developmental phases of the universe. In the first moments after the Big Bang, the universe was a hot, dense mixture of primordial particles. Over millions of years, the first stars began to form, setting the stage for the creation of galaxies. This process of cosmic evolution, from chaotic beginnings to the structured universe we see today, is thought to have taken around 1 billion years. However, observations made by the JWST challenge this timeline, revealing galaxies that appear too advanced for their cosmic age. Instead of observing numerous small proto-galactic fragments merging to form larger galaxies, as current models predict, the JWST has identified galaxies that are already massive and luminous. Follow-up observations using instruments like the Atacama Large Millimeter Array, ALMA, in Chile have provided further evidence to support the existence of these distant galaxies, ruling out the possibility that they are low-redshift interlopers. These groundbreaking discoveries offer new insights into the early universe and may require adjustments to our current cosmological models. The JWST continues to reshape our understanding of cosmic history, questioning long-held assumptions and expanding the frontiers of astronomical exploration. The lack of detectable dust in the galaxies observed by ALMA further complicates the task of verifying the findings made possible by the JWST's advanced capabilities. As Rohan Natu pointed out, while the JWST can follow up on its own observations, ALMA's challenges in detecting these galaxies highlight the complexities of confirming such discoveries. The implications of the JWST's findings are profound, potentially challenging the lambda-CDM cosmological model and prompting revisions to our understanding. Some scientists, like Michael B. and Cullen, have expressed astonishment at the results, suggesting that they may signify a major departure from our current understanding of cosmology. One controversial theory that could explain these findings is modified Newtonian dynamics, MOND, which questions the existence of dark matter and offers alternative explanations for observed gravitational phenomena. Observations from the JWST that align with MOND's predictions have intrigued its proponents, including Mark McCluck, who sees this as further support for the theory. However, some scientists remain skeptical, such as JYP, who highlights the challenges of reconciling these discoveries with existing data. Alternatively, the absence of dust in early galaxies might offer a simpler explanation for their brightness, complicating efforts to accurately measure their masses. Andrea Farrer suggests that dust may not have had enough time to form in the early universe, or it may have been expelled during galaxy formation. Char Mason and her colleagues propose that the JWST may primarily detect the brightest young galaxies, which are easier to observe. David Spergel theorizes that the rapid formation of high-mass stars in the early universe could account for the brightness of these galaxies, proposing that early magnetic fields might have played a role in triggering star formation. The swift influx of scientific papers resulting from the JWST's initial observations underscores the significance of these findings and their profound impact on our understanding of cosmology. As researchers continue to analyze the data from the JWST, they may uncover further insights that challenge and broaden our comprehension of the universe. When the first data began to emerge from the JWST, astronomers were eagerly awaiting the results. Many had been preparing their data analysis pipelines for years in anticipation. Instead of following the traditional peer review process, which can take months, astronomers opted to share their findings on AR-14, a platform where scientific papers can be uploaded for minimal review before formal peer review. This approach has fostered a new form of peer review that occurs in near real time on platforms like Twitter and other social media channels. Rohan Natu described this process as science by arrival, and the ensuing discussions were intense and surprising. Nancy Levinson, the interim director of the Space Telescope Science Institute, STSCI, admitted that she had underestimated the scale of the activity. However, concerns have been raised about the potential drawbacks of this rapid dissemination of findings. Claus Pontypool, the JWST project scientist at STSCI, observes that while quick sharing of results allows for immediate publicity and debate, it also carries the risk of hasty conclusions.